Okay, hello. I'm a science designer, which means I work with lots of different kinds of data, from medical to astronomy. And today I'm really excited to share with you guys this collection of 10 maps that I designed using open data from NASA and the USGS mostly. So this is a personal project that I worked on for several years. And my goal here was to take all of this disparate data sets and combine them into a collection of maps that could really share the science with the general public. So as a science designer, I really like this kind of data translation project, and it's something that I do pretty frequently. So today I want to talk about some of the things I've learned from making these maps using this open data. First, I want to talk about how I developed the design style for this project, and then talk about two of the maps that were particularly hard for me and how I kind of worked through those issues and challenges with the data. So when I first started the project, my first problem I wanted to solve was to find a design style that would tie together these data sets that were collected years and sometimes even decades apart. And I was particularly inspired by this kind of 18th century map. I really love the kind of blank edges on these maps, the way we still didn't really know much about Antarctica or the deep oceans, and you can kind of see at the top where the people just stopped drawing the lines because this particular person didn't know what was there. And to me, right now, space is kind of like the way the world was hundreds of years ago, when we really didn't know very much about it and we were still exploring the geography of our neighborhood. So my goal for the design of this project was to use this style to tie together our history of exploration with what we're doing today. So this is my very first map in the project, where I started exploring this design style with a topographic map of Mars. And this was actually a very time-intensive project that I drew mostly by hand. So it was a learning experience in that it pointed out that I needed to learn some better mapping techniques to really be able to design the kind of space atlas I was looking for. And to explain a little about what went into that map, this is the original topographic map from NASA. So to make my map, I printed this out, and then I traced each of the topographic lines by hand. So each topographic level is traced on a different sheet of tracing paper, which I scanned into Photoshop and then colored each layer again by hand. And then I also found a different relief map from NASA that I overlaid on top for a little bit of texture. But probably the most time-consuming part of this map was I wrote all the labels by hand and curved them all, and also spell checking every single proper noun was very, very time consuming. So in the end, I did like how the map turned out, but I needed to really find a way to figure out this time problem where I wasn't spending so much time on just one map. So this is my second attempt. And my main focus for this map, this is a map of Venus and the origins of each of the names. So when I made this map, I was really focused on trying to solve this time issue and trying to figure out a better way to make maps quickly. So I changed my design style to a kind of Cold War, space race-inspired visual style. And my idea was that I wouldn't have to hand draw the topographic lines by hand. But it turned out that most of the time I spent on this map was still on the labeling and the individual labels. So it really didn't end up saving that much time, or at least enough to make this feasible. So at this point, I kind of put the project on hold for a bit. I couldn't really figure out a good way to get past this, and I worked on medical infographics for a few years. But then I went to grad school and I learned how to code in Python. And then for me, this was really this huge change in how I learned to design using data. So the biggest difference was definitely in the labeling. So now, instead of labeling each thing by hand, I'm pulling the label data from NASA and plotting them in the correct location and the kind of approximate font sizes that correspond to the feature. I also didn't have to rely on the projections and illustrations that were published by NASA. Instead, I could download the raw digital elevation model, reproject it into whatever configuration I wanted, and then change things like the shadow angles, the lighting. I could also use this data itself to pull out the topographic lines instead of drawing them by hand, and fill them in using the color gradients I was looking for. So there was still a lot here that I designed by hand. The scrollwork borders are designed by hand. The maps here, I combined the layers in Photoshop using various overlays. And then there's also kind of a sphere shadow effect added to the on top of the final map to make it look a little bit more like a sphere. But even those time-consuming hand illustrations, in the end, it turned out to be much less work when divided over maps. Because for me, the biggest impact of learning how to code was that this map didn't have to be a standalone map. So all of my code is open source, but to show you a little bit, all of the things that kind of define that Mars map is contained in one configuration file in just a couple of lines. So if I wanted to make another map of Mercury, I really just had to add a few more lines of code, changing out the data sets, and then very quickly and easily use the exact same code as for Mars to make a map of Mercury. Or for example, the moon, where most of the craters are named after famous scientists and artists and explorers. And I could even expand the original code to quickly branch out and build on top of what I already had to more quickly try new kinds of designs. So, and this learning process was possible first because of the open data, but also because of all the open source code that people published, and for working with these data sets in Python. So this was really an amazing learning experience for me. But of course, working with code to use open data comes with its own set of problems. So I want to share with you two maps that I designed where I struggled the most with dealing with this data. So, and this first map shows about 18,000 asteroids in the solar system. And from the very beginning, I think this was my most technically challenging open data project, because to even get this data, I had to combine about 5 different data sets and learn how to use the NASA orbital mechanics server. But then when I got the data, it actually looked kind of like this. And the problem here is that most of the asteroids in the solar system are concentrated at the very, very center, so that if I wanted to map the entire solar system in a static map, it really wasn't legible in any way. So I did want to make a static map. I wanted to print it. I think the obvious solution would be to make this interactive, but that, for various reasons, was not the case. So the biggest change I made to this data was to take all these data points and reproject them into a radial logarithmic scale instead of the linear scale that I was showing you earlier. So this really put the emphasis on the first 1 billion kilometers or so from the sun in the solar system, where most of the asteroids are in the main asteroid belt. But I could still show the many asteroids in the very outer edge of the solar system in the Kuiper belt, which I also thought was an important feature of the solar system. And my second problem was visualizing the size of each of the asteroids. So here, I've scaled up the size so that you can see the smallest ones on the map. But I've scaled everything linearly. So you can see that there's really a huge range in the size of these asteroids. So for example, in the lower left-hand corner, that's Pluto. And on the entire map, it actually would cover basically the entire lower quarter of the map. So to make this data more legible, what I decided to do was to use a different logarithmic plot to scale the asteroid sizes in a little more manageable way. So this does get rid of the original range in size. That's also very interesting. But what I was really trying to do with this map is make a kind of legible screenshot of the solar system. So I thought this solution still kept a little of the relative size of the asteroids without the overplotting problem. There are also a lot of asteroids in the solar system where we don't know the exact size. So those are the dashed lines in this map. Actually, I think, let's see. Okay, so it turns out there's about 63,000 asteroids where we don't know the actual size, and that was too many things for me to plot. So I actually ended up pulling out 8,000 random orbits from this data set, and then plotting them as these dashed lines following their orbit. And I really wanted to make sure I included these asteroids in some way, because as you can see, most of the ones where we don't know the size are in the outer solar system. And even if we don't have as much data about that section of the solar system, I thought what we did have was pretty interesting. Okay, and finally, I wanted to show the actual orbit paths of each of the asteroids. So the scatter points are plotted at the asteroid's location on New Year's Eve in 1999. And I also had the data for where the asteroids were at all these days previously. So my first attempt was to make the length of the orbit tails the same length for all the asteroids. But you can see that the ones on the inner asteroid belt cover so much distance on this logarithmic map that this really didn't look like anything much when I plotted them all in this way. So instead of making each orbit tail the same length, I decided to cap the maximum length to be a quarter of the object's orbit. So in the final map, the orbit tails reach for a maximum of 40 years, or capped to a quarter of the object's orbit. Labeling the map also took a little creative problem solving. I certainly didn't have enough space to plot all of the names, so I manually went in and pulled out the names of interesting asteroids, like the biggest ones or the ones that we've explored with spacecraft. And I wrote some custom code to make these labeling lines a little bit easier to design in Illustrator. Okay, so this final asteroid map is, well, it's certainly not an exact reflection of reality, but it's a mix of many different technical solutions that I cobbled together to solve these different problems. Okay, so you can't really see this map very well, I'm sorry about that. But another issue I often run into is open data is kind of the problem of having way too much data for one map. So then I have this problem of trying to decide what to keep in and what to leave out. And I think this constellation map was probably the map where I had the most data that I took the most out in the final map. So the very first thing I did is the open star database I used had hundreds of thousands of stars. So to even make the map legible, I decided to clip out everything except the 8,000 or 9,000 or so that we can see from Earth with the human eye. But even after taking out all of these stars we can't see, there's still a lot of information for each star. So each star has an approximate color. Of course, it has a location. It also has an approximate magnitude, the apparent size from Earth. Oh, what am I doing here? OK. And then, since this was a constellation map, I also wanted to include the boundaries of the astronomical constellations. So in astronomy, a constellation is a little bit different from what I think we colloquially call a constellation. So the red boundaries of the sky here are what are the official constellations. These patterns in the sky are called asterisms. And I also wanted to include these because they're a little more familiar and we understand those shapes. I also wanted to label the shapes and add other things in green, like nebulae and galaxies that we can also see from Earth. So at this point, this is the final map for one of my designs. And it might look like there's a lot of data on this map, but I did actually take out quite a bit. And I think in many projects as the designer, I end up in a kind of position of deciding what data is important and what isn't important. So I really try to make sure I think about that. I think it's a particularly important consideration when making science designs. because my choices can really affect how people look at the science. So as an example, this map that I'm showing you, it shows the traditional Western patterns in the sky. But these asterisms, or the colloquial patterns, aren't scientific facts about the stars. Obviously, the stars aren't actually connected in this way. So I could have shown you the traditional Arabic patterns, and the map would have been just as accurate, or the traditional Chinese shapes, or the Korean ones, the Hawaiian shapes, or a combination of star patterns from every single culture I could find from this open data set called Stellarium. So this is about 30 different cultures and civilizations throughout history. So this is the second map I made. I made 2 maps for this project. And this one shows, I wouldn't really call it a map. I'd really call it more of like a visualization of how everybody around the world has been really fascinated by astronomy throughout history. And I'm not saying either one is like the correct data selection, but I think this is a good example of how my own perspective in looking at the data and how I select data can really affect what other people see in the science. So I think for me that's a really important challenge and a very difficult one to navigate, because in the end I think these stories that we show with the data are really what's most important in connecting with people and serving as kind of the gateway for people to be interested in the science. So thank you. And as a final note, all of my code is open source. Please feel free to download it and use it. All of it comes with a tutorial that explains what I did with the code. If you go to my GitHub page, it also has links to all of the open data sets I used. So thank you to everybody who makes this open data available and possible for people like me to play with. And thank you all for coming and listening to me today.